Hello, everyone. In this section of electronics, we will introduce the operating concept of MOSFET amplifiers. The circuit on the slide is a basic MOSFET amplifier. The input voltage is applied at the gate, and the output is taken at the drain. When the MOSFET operates in the saturation region, the drain current is given by ID equals 1/2 Kn times the square of the quantity VGS minus VTN. In this expression, the entire term VGS minus VTN is squared. This means the current is controlled by the gate-to-source voltage, so the MOSFET behaves as a voltage-controlled current source. When VGS increases, ID also increases. As a result, the output voltage VO, which is equal to VDS and also equal to VDD minus ID times RD, decreases. Next, let us look at the transfer curve between the input voltage VGS and the output voltage VDS, as shown on the right. First, when the input voltage VI, or VGS, is less than VT, the inversion channel is not formed. Therefore, the MOSFET is in the cutoff region and ID is 0. Since there is no voltage drop across RD, the output voltage VO, which equals VDS, is equal to VDD. This corresponds to point A in the figure. When the input voltage VI, or VGS, becomes greater than VT, the inversion channel forms and the device turns on. The drain current ID begins to increase as VGS increases, so the output voltage VO begins to decrease. As discussed earlier in the ID versus VGS characteristic, just after VGS exceeds VT, the overdrive voltage VOV is still small, so the device operates in saturation. As VGS continues to increase and VO continues to fall toward point B, the device is about to enter the triode region. Therefore, between points A and B, the MOSFET operates in saturation. The slope of this segment, AV equals dVDS over dVGS or dVO over dVi, is the voltage gain. From point A to point B, ID equals 1/2 Kn times the square of VGS minus VTN. Therefore, VO equals VDS equals VDD minus ID times RD, or VDD minus 1/2 Kn times the square of VGS minus VTN times RD. From this curve, we can see that the largest slope occurs in the saturation region. That is why MOSFET amplifiers are usually biased to operate in this region. At operating point B, the MOSFET is at the boundary between the triode region and the saturation region. At this boundary, VDS equals VOV, which is VGS minus VT. Therefore, VDS at point B equals VGS at point B minus VT. Also, VDS equals VDD minus 1/2 Kn times the square of VGS minus VT times RD. Substituting the boundary condition gives the expression for VGS at point B. VGSB equals VT plus the quantity, square root of 2 Kn RD VDD plus 1 minus 1 divided by Kn RD. Here the term 2 Kn RD VDD plus 1 is inside the square root, and the denominator is Kn RD. Because a large voltage gain is obtained when the MOSFET operates in saturation, the DC bias is chosen so that the device operates at point Q, as shown in the figure. This point is called the bias point, the DC operating point, or the quiescent point. At this DC operating point, with DC values VGS and VDS, a small input signal VGS can be applied at the gate, and a small output signal VDS can be obtained at the drain. The signal gain AV equals VO over VI, which is the same as VDS over VGS. It's also equal to dVDS over dVGS at the operating point. In other words, the voltage gain is the slope of the transfer curve at Q. When the input signal amplitude is small enough, the output signal VD, or VDS, is approximately proportional to the input signal VI, or VGS. Therefore, we differentiate the output equation VDS equals VDD minus 1/2 Kn times the square of VGS minus VTN times RD with respect to VGS. This gives the voltage gain AV equals negative Kn times VGS minus VTN times RD. The negative sign means the input and output signals have a 180-degree phase shift. The gain is proportional to Kn, VOV, and RD. Since ID equals 1/2 Kn VOV squared, the gain can also be written as negative ID times RD divided by VOV over 2. The maximum magnitude of AV occurs near point B, where ID times RD is largest. However, in practice, we usually do not bias exactly at point B, because after adding a small signal to the DC bias, the device may enter the triode region. That would change the gain significantly and cause output distortion. We can also use graphical analysis to understand how the operating point Q is chosen. In the figure, the horizontal axis is VDS and the vertical axis is ID. The blue curves are the MOSFET ID versus VDS characteristics, and each curve corresponds to a different input voltage VGS. The resistor RD also has its own ID versus VDS relation, given by ID equals VDD minus VDS divided by RD. This can be rewritten as VDD over RD minus 1 over RD times VDS, which is a straight line. This red straight line is called the load line, and its slope is negative 1 over RD. The intersection between the load line and a MOSFET characteristic curve is the operating point. Therefore, for each value of VGS, there is a corresponding operating point. This is essentially the simultaneous solution of the voltage-current equations of the transistor and the load resistor. Thus, the operating point is determined by both VGS and RD. For logic circuits, the input voltage usually has only two levels, 0 volts and VDD. Therefore, the MOSFET mainly operates either at point A, where VGS equals 0 volts, which is less than VT, so the transistor is off and VO equals VDD, or near point C, where VGS equals VDD, the drain current is high and VO is low. This behavior matches the high and low states, or 0 and 1, used in digital logic. For a voltage amplifier, however, the circuit is an analog circuit, so the device should be biased in the saturation region. Ideally, the DC operating point Q is chosen near the middle, around VDS equals VO equals 1/2 VDD. If the operating point is chosen near Q1, the maximum output voltage VDD is too close to the DC output level VDS1. This limits the maximum positive swing of the output signal, and this upper voltage margin is called headroom. Similarly, if the operating point is chosen near Q2, the DC output voltage VDS2 is close to the triode region. This limits the maximum negative swing of the output signal, and this lower voltage margin is called legroom. In addition to the choice of VGS, the choice of RD is also important. A smaller RD moves the operating point toward Q1, while a larger RD moves it toward Q2. This bias point selection concept is similar to what we discussed for BJT amplifiers. This concludes our introduction to the operating concept of MOSFET amplifiers. Please look forward to the next section. See you next time. Bye-bye.